Hello, and here we are to do some nuclear physics problems today, and we're in chapter 32, looking first at number 6, and part A is asking what initial kinetic energy must an alpha particle have if it is to approach a stationary gold nucleus to within a distance of 25 FM. And so we're looking at kinetic energy going into electric potential energy. So 1/2 mv squared equaling qv. And the v comes from the gold nucleus, so this could be little q times big Q, k over r, where this part is representing that initial voltage. R is 25 FM, which F is times 10 to the minus 15th meters. And so if we go through and do, for the helium nucleus, the mass would be, there's 2 protons and 2 neutrons so I'm able to find the total mass of the helium to be 6.695104 times 10 to the minus 27 kilograms. So I set up 1/2 times that mass, 6.695104 times 10 to the minus 27 kilograms times velocity squared, set that equal to k, 9 times 10 to the 9th, q1, where little q here is 2 times the charge of a proton, so 2 times 1.6 times 10 to the minus 19 coulombs. And the charge of the gold nucleus would be 79 times the charge of the proton, 1.6 times 10 to the minus 19. So that's k, little q, big Q, or q1 and q2, however you want to say it, divided by the distance of 25 times 10 to the minus 15 meters. From that, we get the velocity would have to be 219.8 meters per second. And for part B, the question goes on to ask, by what factor is the distance of closest approach changed if the initial speed is reduced by a factor of 2? So if you do 1/2 mv over 2 squared equals kq little q over r, the idea is that if you're 1/2 the speed, that speed squared, the radius would have to be 4 times greater. You couldn't get as close, so it's 4 times the initial radius. The second problem I wanted to look at was from chapter 32, number 17. And here we've got a reaction. Just as a heads up, I use Appendix F in your textbook to get some of the numbers here, and we're going to even check that out. So for 32, and I will just, or number 17, I'll just do part A, because part B then you guys can try on your own. Part A has 212.84 PO going into alpha decay. So what would be left over, 212 minus 4, would give me a 208 on top and 82 on the bottom. And when I go to Appendix F to look this up, I'll even show this to you guys. Appendix F kind of looks like this. And if we go to 208.82, we'll notice right here, it is lead. And if you look up lead and 208, I can get the atomic mass for that. PB. And I had already found the atomic mass for the polonium and the alpha nucleus, and for the lead, that's 208, this is 207.97664. So from that, you are able then to find each of these parts and the amount of mass that is sort of missing here. And so the change in mass I end up getting is 0.009609 U. And if I convert that from U to kilograms, where 1 U we're having technical difficulties. Okay. 1 U is 1.66 times 10 to the minus 27 kilograms. I can then get how many kilograms this is and do E equals mc squared. So if I were to get the number of kilograms, 0.009609 times 1.66 e to the minus 27, 1.595 times 10 to the minus 29 kilograms times c squared. C is just 3 times 10 to the 8th, obviously. And we're able to get 1.43558 times 10 to the minus 12 joules of energy in that reaction. Then I wanted to look to our packet and do some of these ones from the nuclear packet. And here, we'll just try the last row again. If you are decaying, alpha decay, and you're getting thallium, then this must have started with 207 plus 4 or 211 on top. And on the bottom, 81 plus 2 would be 83 on bottom. And if you look this up, that would be bismuth. If we had magnesium and 1 neutron, so you had 25 total at the top, now you're going to have 1. This is 24. And let's see on the bottom, you had 12, now you're going to have 11. That makes this sodium. If you wanted to do, like number 3, a lithium isotope has a nuclear mass given here, calculate its mass defect and its binding energy. Remember, the mass defect is the difference between the mass of the parts, where there's 3 protons, 1.007825 AMU, and there's 4 neutrons, 1.008665 AMU, and compare that with the original mass, which was 7.016005 AMU, and the difference would be 0.042130 AMU. This is called the mass defect. Then if we want to find the energy associated with this, again, E equals mc squared. So we take this energy, I'm going to convert this mass into kilograms. So I'll take 0.042130 times 1.66 times 10 to the minus 27 kilograms per U times 3 times 10 to the 8th meters per second squared. And I'm able to get that the energy would be 6.294222 times 10 to the minus 12 joules. Then the last one I was going to look at is one of these half-life ones, where if it took 1.5 hours for 12 grams of a material to decay until 1.5 remains, the idea is we started with 12 grams. One half-life goes by, now you've got 6 grams. Another half-life goes by, you've got 3 grams. Another half-life goes by, you've got 1.5 grams. So we've gone through 1, 2, 3 half-lives for this material. And if it took a total of 1.5 hours to go through 3 half-lives, that means that a half-life has to be equal to 1/2 of an hour. Thank you so much. Bye-bye.